All right, let's get started. Final reminder for you, exam tomorrow night, 6:30, Hall of Music, same place, same time as usual. Get there, we're going to start at 6:30 sharp because many of you have an exam right after hours. So we got to start on time so we can end on time. So we'll start at 6:30 sharp. If you show up late, we'll start without you, okay? Another announcement about SI, if you want to go to SI session, there is one today, 5:30 to 6:20 in Weather Row 420. The leaders, Nick. And tomorrow there is also one, 4:30 to 5:20. Brittany is the leader tomorrow in Shreve Resource Center, C113. Calendar, we're doing review today. Tomorrow, recitations, more review. Bring whatever question you want to go to recitation. No quiz tomorrow in recitation. There is a class on Friday, like I mentioned a few times. However, there's no class next Monday, and there's no recitation next Tuesday. Finally, on the course page, there's a study guide that I posted a few days ago. It just outlines the major concepts that you need to know. So use this as kind of a reminder of things that you need to know, okay? All right, so today, just like the last couple of times, we're going to go over a few old exam problems I have chosen that cover the concepts that you need to know for your exam tomorrow. So let's start with the hardest part of the exam, the related rates. In this problem here, we have a ladder, 8 feet long. It's resting against a vertical wall. If the bottom of the ladder slides away from the wall at a speed of 2 feet per second, how fast is the angle between the top of the ladder and the wall changing when the angle is pi/6? All right, so let's see what's going on here. That's the wall, that's the ground, right? And then here's your ladder that's 8 feet long. As the bottom of the ladder is being pulled away, both the distance from the bottom of the ladder to the wall, this distance right here, and the distance from the ground to the top of the ladder are changing as time goes on. So those are not constants. Give them names. You got to give stuff names that are not changing. Let's call this thing right here x, call this thing y. So x is representing the distance from the bottom of the ladder to the base of the wall. Y is representing the distance from the top of the ladder to the ground. What we know, the only thing that we're sure to be constant is the length of the ladder. If the bottom of the ladder is sliding away, that's a very important part of that statement. That means that x, the distance x, is lengthening over time, getting bigger. That means the rate of change of that quantity with respect to time is a positive rate. If you're pulling the ladder toward the wall, then this will be a negative distance, negative rate because the distance is shrinking. We want to know more about the angle between the top of the ladder and the wall right here. Let's call that angle theta. How fast is the angle between the top and the ladder of the wall changing? How fast? That's a rate. So we want to find the rate of change of theta, d theta dt, at the particular moment when theta is pi/6. Okay, the key to these related rates problem is to keep track of what is changing, what is constant almost nothing is constant. The only constant is that 8, the length of the ladder. Everything else is changing. And you don't deal with any of those numbers until you set out the problem, taking a derivative. We're trying to relate the rate of change of x to theta. So let's relate x to theta. We have x, we have y. We know nothing about y, so we don't want to get y involved. We know something about x. So let's relate x to theta by taking advantage of the fact that 8, this constant 8, is the length of the ladder. Leave y out of it. We want to relate the opposite and hypotenuse, right? So sine is a good one to do. Sine of theta, the opposite over hypotenuse, x over 8. Now we've gotten a relationship between the two. We take one derivative with respect to time. Left-hand side is cosine of theta. Remember the chain rule, d theta dt. Right-hand side is 1 over 8 times dx dt. Now we can put in these numbers. Now we can deal with what else is going on here. So let's see. D theta dt is equal to 1 over 8 cosine of theta dx dt. You don't deal with that when a theta is pi over 3 business until after you've gotten a derivative. When theta is equal to pi over 6, d theta dt is 1 over 8 times cosine of pi over 6 dx dt. We know cosine of pi over 6. We know dx dt. And now it's just a matter of simplifying this stuff. So let's see, we get 2 over 4 radical 3, or 1 over 2 radical 3. And that would be radians per second. All right? Questions? Okay, so make sure you track what is constant, what is not constant. Don't throw too many numbers in there. The only thing that you knew that stayed constant the whole time was the length of the ladder. That's it. And by the way, notice we didn't know anything about y, and we didn't need to know anything about y. We did everything there without any knowledge about y. All right, let's do another one. Another related rates. Let's do a tank. Yeah. Normally, when we're presented with a cone, it's the wide end at the bottom. When you say it's inverted, that just means it's like a funnel, basically. You pour water in through the top, the open end, and water comes out. Okay, I got asked this question so many times during office hours, so Well, a question similar to this cone thing. So, it's a good one to work out. We got our circular cone with base radius of 2, so let's sketch it. Just a rough sketch. Radius is 2. All the units agree, so we can ignore them. And then height is 4. This thing is leaking water at this rate. So water is coming out of it. At 5 cubic feet per minute. If water is being poured into the tank at the rate of 7, so poured in at 7 cubic feet per minute. We are interested in finding the rate at which the water level is rising when the water is 3 feet deep. All right, so remember, you got to consider this little portion of the cone that represents the water already in the tank. It has a certain height, which is always changing with time. It also has a certain radius. That is also changing with time. So look at the way I labeled my pictures. The only things I knew were constants, were the radius, the height of the tank, the rate water is going in, the rate water is coming out. Everything else is changing with time, so they receive variables. All right, so what do we want? We want the rate at which the water level is rising, the rate of change of the water level, h, at the particular moment when h is equal to 3. So it's nearly to the top of that. All right, so let's write out the volume of the water. V is equal to volume of that little green cone in here. This old exam didn't give the formula for the volume, but if this problem were to show up on your exam, we would give you the volume of that cone. Okay, you need to know really basic stuff. We won't give you the formula for a box or a circle or stuff like that, but things like a cone, a sphere, more exotic stuff will give you the formula. So anyway, it's 1/3 pi r squared h. That represents the volume of that green portion inside there. Okay? Let's reduce this down to one variable. We want to know more about h, so we want r to go away. Let's eliminate r because we want to know more about h. If this thing were asking about the rate of change of the radius of the water surface, then you would get rid of h because you want to know more about r. All right, we've done this before. If you take a slice of the front view of the cone, we would see half of it would look something like that. So here, this is representing the water already in the cone. The top here, this is representing the radius of the cone, and then the long side is representing the height of the cone. This is representing r, and then h is the height of that smaller triangle. Okay? Then we can use similar triangles to relate R and H. We know the ratio of R over H must be the same as the ratio of 2 over 4. That tells us that R is equal to 1 over 2H. In other words, no matter how high the water level is, the radius is always 1/2 of that. As time goes on, that ratio is maintained, even though H is always changing. But R will change this together in this way. Go back to the volume equation. Now we can get rid of R. Get rid of the R and put in 1/2 H. So we end up getting 1/3 pi times 1 over 4 H cubed, or 1 over 12 pi H cubed. Any questions so far? And really, once you got down to here, the rest of this is pretty straightforward. All the work on related rates problems are up from setting the problem up. You don't set it right, you won't get it right. But once you set it right, usually what follows is not the most difficult thing. Okay, let's take a derivative. I'll rewrite that equation here. The rate of change of the volume with respect to time is equal to 1 over 12 times pi times 3h squared. Remember the rate of change of h also because of chain rule. And that gives you 1 over 4 pi h squared dh dt. The rate of the change of the volume, dV dt, we're pouring 7 cubic feet per minute in, we're taking 5 out. So the net change is a 2, right? It's physically the same as if we just have a closed tank and we pour 2 cubic feet per minute in. It's exactly the same. 7 in, 5 out. So that's a 2. 2 goes on the left. On the right-hand side, now we're interested in a particular moment when h is equal to 3. Now we can put in h equal to 3. H is equal to 3 does not come into play until after the derivative. If you put it up front, when you set it up, the answer would be wrong. And the only thing you don't know here is dH dt, so that's pretty easy to solve. That's a 9. That's a 4. 9 over 4 goes over the other side is 8 over 9. 8 over 9 pi. So that's C, looks like. And that would be feet per minute, of course. Okay, questions? Okay, make sure you also review all the other homework problems on related rates that you saw. You also saw the guy walking away from the light toward the light, that kind of thing. We saw boat going away from a dock, the other one going to the dock, that kind of thing. And what else did we do? The trough. Trough is very similar to this cone. It's kind of almost the same kind of problem. The ladder one we did earlier. And what else? Oh, airplane flying horizontally, ground station, blah, 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 that kind of thing. Review all of those problems. Make sure you know how to do all of them. All right, so we got the most difficult part of the thing out of the way. We'll look at slightly simpler stuff. The next two big topics are the first and second derivative tests, right? You got to be able to find the critical numbers, the max and min, concave up, down, increasing, decreasing, inflection points, all that stuff. I got a few problems here to review that. Okay, so in this problem here, we want to find how many critical numbers. So of course, you got to remember what a critical number is. A critical number is where the first derivative is equal to 0, or when the first derivative does not exist, but is in the domain of the function. This kind of thing often happens with root functions. You take the derivative, you find out where f prime does not exist, but the number also happens to be in the domain of f of x. Luckily, we got a polynomial here. So the second criterion will never happen. Only the first one matters. F prime is always defined. Okay, let's take one derivative. 7x to the 6 plus 14 equal to 0. Now we solve for x. Right? Subtract 14 divided by 7, so x to the 6 is equal to minus 2. So what's the answer? How many critical points do we have? There aren't any, right? Because? Correct. Right, we don't worry about I here. We'll deal with I in 162. Little bit, not too much. This has no real solutions. So that means f prime is never 0, and f prime is never, does not exist. We don't get anything out of that. That means we have no critical numbers. So what does that mean in terms of relative max and min? If this is our conclusion about critical numbers, what does it tell us about relative maximum and relative minimum? There aren't any, correct, because the only places where relative max and min can occur are at the critical numbers. If there are no critical numbers, then this thing will never stop growing or stop decreasing. So there will be no relative max or min. Any question on this one? Good. All right. Oh yeah, there's also the mean value theorem. Well, let's take a look at it. Given the function f of x is equal to x cubed minus 3x plus 5 on the interval minus 1 to 1, the number or numbers A that satisfies the conclusion of the mean value theorem is 5 choices. Of course, this problem will be entirely impossible if you don't know what the mean value theorem tells you. The mean value theorem says if you got a function f of x on the interval, closed interval a to b, that is differentiable on the open interval a to b. The fact that we got a polynomial means that is both of these conditions are satisfied, right? Then the mean value theorem says the secant line slope from the beginning to the end is going to be equal to tangent line slope at some value of c, where that c is somewhere between a and b. Yeah, you're right. It has to be continuous and differentiable. So it's both true. So it's okay. You're right. Absolutely. Let me write that there. But again, the fact that we have a polynomial means it is automatically continuous. It is automatically differentiable, infinitely differentiable. So the secant line slope is equal to the tangent line slope at least one place. There's at least one c between a and b. So let's see. Let's find out the secant line slope here. Our b is the right end. A is the left end, of course. Calculate the secant line slope first. F of 1 is 1 minus 3 plus 5. So that's a 3. Right. F of minus 1 is minus 1 plus 3 plus 5. So 7. Downstairs is a 2. So that's a negative 2. That's the left-hand side. Right-hand side is the derivative. F prime of x is equal to 3x squared minus 3. And we know the theorem guarantees that this will be equal to the secant line slope at an x value somewhere between minus 1 and 1. So what do we see? We see x squared is equal to, at 3 divided by 3, 1 over 3. So x is equal to 1 over root 3 or negative 1 over root 3. Got to make sure both of these things are inside the interval. Minus 1 to 1. Okay. 1 over root 3 is about 0.6, roughly 0.6. So that's positive 0.6, negative 0.6. Both are within the interval. So we would choose A. Right? Both are in minus 1 to 1. Okay, in other words, the theorem just guarantees that there's at least one inside the interval. There could be more outside, but the theorem doesn't say anything about the ones outside. Just guarantees at least, possibly multiple, within that interval. How is the mean value theorem different from Rolle's theorem? Right. Right. Rolle's theorem just says that the two endpoints have the same y value. So they're at the same height. Therefore, it says at least one place between the two endpoints where the slope of the tangent line is horizontal. That's the difference between Rolle's and mean value. But mean value theorem is a generalization of Rolle's. It contains Rolle's theorem inside here. So if you only know one, then the mean will be good enough. Questions on this one? All right, let's move on. Okay, this one we should be able to do very quickly. This is a pretty straightforward one. We're looking for the absolute max and min. And you know we're looking for the absolute because this is a closed interval. So we get absolute max and or min of the function out of it. Here we're looking for both the max and the min respectively. All right, so you know how to do this. Take one derivative, set equal to 0, find the critical numbers. And the only thing that you really got to watch out for is that the critical numbers you get out of this has to be within the interval. Anything outside that you automatically reject. We only care about -3 to 3. This tells us our critical number is -2. -2 is clearly within that interval. Excellent. So now we check the value of the function. Add the critical number, possibly multiple, and the two endpoints. We want to see what happens at -3, what happens at -2, what happens at 3. The next thing to watch out for is which function you're plugging numbers into. You got to find out what the value of the function is. F prime has served its purpose. We don't deal with it anymore, right? We don't deal with that. These have to go back to what you started with. So what do we get? We get -3 squared, that's 9, -12, -3, so this is a -6. -2 into here is +4, -8, -3, so that's a -7. 3 goes into here, we get 9, plus 12 minus 3, and that's an 18. The largest of these three is the absolute max. The smallest of these three is the absolute minimum. Okay, max at 18, min at -7. Yeah, this one. Oh, because you could rationalize this. This is the same as 1 over √3 times √3 over √3, and that's √3 over 3. Let's check out this one. Another polynomial function, 2x cubed minus 3x squared. We're looking for how many local max and min it has, and how many inflection points it has. We know how to find the local max and min. Inflection point, remember the definition of that is where the second derivative changes sign. Essentially, you're finding the increasing, decreasing intervals and the concave up and down intervals. Once you have those two things, these fall out automatically. Start with the first derivative. Set equal to 0, find the critical numbers. Take out a 6. And this tells me x is equal to 0 and x is equal to 1. Then we check the sign of f prime to the left and to the right of each of these critical numbers. Positive means increasing, negative means decreasing. Choose any number less than 0. Let's say minus 2. That's negative 12. That's negative 3. Product of two negative numbers gives you a positive number. So that thing is increasing here. Between 0 and 1, this will be positive, this will be negative. So this is decreasing. Greater than 1, we get positive, positive. So it's increasing here. Increasing, decreasing, then increasing. So it went through two sign changes. This has one local max. At x is equal to 0. One local min at x is equal to 1. Now we repeat that same exercise with the second derivative. So we see x is equal to 1/2. We'll make f double prime 0. Duplicate the same thing. X is 1/2. Now we check the sign of the second derivative. Do the same thing. Choose some number less than 1/2. Say 0. 0 goes into here. It's negative 6. That's a negative number. So it's concave down. Choose something bigger than 1/2. Say 1. 1 is positive, so that's concave up. Concave down, concave up. One switch in between. So this means that we have one inflection point. Right? So this problem is identical to finding the intervals of increasing and decreasing and intervals of concave down, concave up. The inflection point is where the second derivative changes sign. You find them by taking the second derivative, make it equal to 0, or f double prime undefined. But just like the critical numbers, they don't automatically qualify to be inflection points or local max and min. You have to see a sign change somewhere for that to occur. Questions? All right, carry on. Okay, the next big topic is L'Hopital's rule. I got two problems here on L'Hopital's rule. The big thing about L'Hopital's rules is that that's not how you spell his name. We can use L'Hopital's rule only if the limit appears to go to 0 over 0 or infinity over infinity. Huh? What's that? Well, we'll get to that, but that's the major, the important thing here. So you see a limit problem, don't automatically jump in there and apply the rule. It is not applicable unless this happens. Okay, now we can check this out. What's going on here? When x becomes very large, natural log of a very large number is a very large number. Natural log of another large number is another large number. So we get infinity over infinity. That means we can use L'Hopital's rule. Okay, just like when I did in class, I'm going to put an h over the equal sign to denote that's what I'm doing here. We apply L'Hopital's rule. X is still going to infinity. We take the derivative of the top and bottom separately. Never use the quotient rule. Differentiate them separately. Natural log of 1 over 1 plus 2x is 1 over 1 plus 2x times 2, right? Don't forget the chain rule. Chain rule is just as critical on this exam as it was critical on last exam. It'll be just as critical on the final exam. It'll be just as critical on any subsequent math class you take. Chain rule is everywhere. Downstairs, we get 1 over 3x. Again, chain rule gives me a 3. Before you jump into L'Hopital's rule one more time, clean this up before you do any more. We have 2 over 1 plus 2x divided by 1 over x. That's equivalent to the ratio at the top multiplying by the reciprocal of the one downstairs. Okay, now when x goes to infinity, you can apply L'Hopital's rule one more time if you want, or you can just reason this and say that when x is large, 1 plus a very large number makes that 1 irrelevant. So really the ratio is just 2x over 2x. Or you can just use L'Hopital's rule one more time. No harm whatsoever. In the end, we get a 1. Okay, so that's the basic L'Hopital's rule problem. Infinity over infinity or 0 over 0. The process is straightforward. Take the derivative of the top and bottom separately. Remember chain rule. Let's look at a slightly more complicated one. The limit as x goes to 0 from the right-hand side. One-sided limits is handled exactly the same way. It really doesn't matter. It's two-sided or one-sided. L'Hopital's rule still applies. So let's see. When x goes to 0, that's a small number. The exponent is also a small number. So we get an indeterminate form of 0 to the power of 0, a small number to a small number power. Depending on which small number goes to small number faster, the limit could be anything. We must somehow change to infinity over infinity or 0 over 0. Then use L'Hopital's rule. Okay? All right, you probably remember this. Let's let y represent the thing whose limit we're trying to find. We want to yank that thing out of the exponent, that x. So we take the natural log. We want to somehow get a fraction out of this, so we can have one of these two. So we can write this as an equivalent form, in the equivalent form as natural log of 3, a sine of 3x. Instead of multiplying by x, we'll write it as a dividing by 1 over x. This way, when x goes to 0, this is infinity. When x goes to 0, this is a negative infinity. So we can apply that rule. Okay, so we see the right form that we want to see. Apply L'Hopital's rule. Limit x goes to 0, derivative of the top, 1 over sine of 3x times derivative of that, sine 3 cosine 3x. Downstairs is 1 over x squared, negative. I'm going to rewrite this a little bit as I can multiply the negative x squared to the top. So minus 3x squared cosine of 3x over sine of 3x. And now this thing appears to go to 0 over 0. And there are two choices. We can use L'Hopital's rule one more time, but that involves using product rule on the top with lots of chain rule. So it's doable, but it's probably not the best choice. The alternative, let me show you, is to separate things out a little bit. Oops, sorry. So look what I did. I kept the sine of 3x downstairs. And from minus 3 sine x squared, I kept 3x on top of that. Now, why did I do that? What good does this do? What does this thing do here when x goes to 0? That goes to 1. Yeah, so that's the reason why I did that. This guy, of course, goes to 0. Cosine of 3x when x goes to 0 is a 1. So the limit is 1 times 0 times 1, and that, of course, is at 0. Is that the right answer? What are we missing here? Right. Right. This is the limit, x goes to 0, of the natural log of y. We want the limit of y, which is this thing right here. So this means that the limit of y is e to the 0, and that's going to be a 1. Okay, about graph sketching, obviously we cannot ask you to sketch a graph on the exam, so you need to be able to identify a given graph or use the information we give you to come up with the right choice of a graph. Very similar to the homework problems you saw on web assignment for that section. You have graphs to choose from, and you have some information about the function. So review the homework on that section, and that should be fine. You won't be sketching anything on this multiple choice exam. All right, that's it. See you tomorrow night.
There's a part where you had this on the video. So, pre-stamp supper tomorrow?